Hello, everybody, and thanks for joining us today. My name is Andy Ellicott from Swarm64, and joined by Sebastian Dressler, our head of solution engineering. For those of you who are new to Swarm64, we are a bunch of performance fanatics that develop software or extensions to Postgres to make it go faster, mainly query processing right now, based in Berlin and United States here in the Northeast. And our agenda today is to talk about ColumnStore indexing. And there are a bunch of ways that we make Postgres query processing faster. As you can see here in the TPCH benchmark, popular data warehousing benchmark. Swarm helps Postgres perform this benchmark about 20 times faster, depending on the hardware you're running on. And a big part of that is columnar storage, which reduces the I/O and the time it takes for the database to scan and filter data. And that's what Sebastian's going to talk about today. Just a quick primer on columnar versus row-oriented storage and the impact that those two things have on query performance and other database factors. Then he'll jump into how the ColumnStore indexing that Swarm implements works for Postgres. Okay, and then we'll wrap up with Q&A at the end. If you have questions during the presentation, feel free to enter them through the questions panel here and go to webinar. One of the most popular questions is, will you be sharing the slides? And the answer is yes. We'll send everybody registered for the event a link after the webinar concludes, link to the recording of this event, so you can catch it if you have to leave early, or share it with colleagues, as well as the slides that Sebastian will present. Next slide. And before I turn things over to Sebastian, just kind of the part of the so what, right? So faster querying with Postgres, what does that mean to people? When Swarm is very often used to accelerate Postgres query performance, it really enables people to do more with Postgres and really kind of address a larger set of data management projects, starting with projects that one might tend to use Oracle or SQL Server for, especially if you're leveraging the ColumnStore index in SQL Server, which is very close to what we've implemented here in Postgres, or the in-memory ColumnStore in Oracle. Those types of database workloads can now run on free open source Postgres, the same kind of performance, which is great. And so that means you're allowed, really now enabled to handle much more easily and much less expensively workloads and database projects that have to support a lot of reporting, especially things with high concurrency. Lots of clients or users querying or running queries against the database at the same time, or where your data volume has grown to a point where standard reporting or charting and graphing has really slowed down. And of course, data warehousing projects, which are some of the most expensive to operate, just because data warehousing databases are database platforms tend to be super expensive. And until now, with Swarm and Postgres, there hasn't been a really great open source data warehousing option for people. So those are the types of projects you can solve with Swarm64 accelerated Postgres, featuring the ColumnStore indexing. And now I'll turn it over to Sebastian for the details on how all that works. Sebastian?
Thank you, Andy. And welcome everybody to the webinar. And I'm going to start with like a very, very high level overview on storage and relational database management systems. So don't be scared. This is not going to be a CS lecture. And of course, there are probably much better people teaching this than me. But let's have a look on like what's typically happening in the background of your database. And we're going to make it really easy. It's just like a decision. Are you more OLTP or is it more OLAP? And depending on that choice, you typically see either a row store or a column store. And as the name suggests, if you're having a row store, then your data is stored across rows. So just imagine any of these horizontal bars here on the left-hand side being one row of data, and typically a row contains multiple columns. And that's just how things are typically also in OLTP storage engines, like Postgres is one, because Postgres is predominantly used for OLTP, obviously. And on the other hand, we have column stores, which were made very popular by techniques like Hadoop with big reduced sets and other column-oriented database engines. And here your data is basically still kind of a row, but you're tearing it apart and you basically connect columns one after another. And then when you start to read again, you predominantly read columns. And if you need to turn these columns back into rows, then you need to obviously know where positions of rows are, and then you can reconnect them. Now, on a typical analytical query, this is not such a big problem because you maybe only select a few columns, not all of them. And then out of those few columns, you will select a few parts of your row. And then the reconstruction of your entire row is not that expensive anymore. But typically, if we are talking about OLTP, on the other hand, again, you are having very likely this row-oriented view, especially when you're writing data. And then in order to reduce this overhead on the other side, you're rather going to have a row store. Now, what happens if we just take those two concepts and we bring them together somehow? And because we are talking about Postgres here, it's just natural to, let's say, we start with a table that is in row storage. Let's just be our Postgres table. And then, in addition to that, we are not going to re-implement this table, or we are not going to change the storage engine where it is backed by, but instead we just add an index on top. And that index now basically adds your columnar view onto your row-like data. And what this results in is what we're talking about today, the ColumnStore index. And this is basically a hybrid model, as you can see, because you're layering things together. So you put this columnar view or columnar storage part above your data. And typically the data is also stored again in your index. So whenever you're reading that index, you get data directly back. It's like a read, an index-only scan in Postgres, if you will. That, however, also has the drawback that if you're having fresh data coming in and your index is not yet up to date, you're having additional rows you might need to read in addition to the columns you just read. And on typical implementations, you will always read the complete column plus any extra rows you might be needing, because your database system, on the other hand, also needs to guarantee you that the data you are asking for is complete and that there are no rows missing, which is just one consistency property of today's database management systems like Postgres is one. Now, why do we care about an index? Because you can keep your data. So you can basically stay with your row orientation, meaning all your transactional properties are maintained. You get good ingest speeds because like the row construction overhead is not so big, as you can simply store the data directly. And you can apply all your constraints across your rows like you used to with your primary keys and unique keys and also foreign keys. Not saying that this is not possible with column stores, but this is just much more difficult, and typically in column-oriented storages, where the table storage is column-based, you in the end forget about these indices because you rely that the data that's delivered to you is already sanitized in the wider sense. But now, if you just put an index on top, then your database guarantees this for you actually. And on top of that, you can, of course, compress the index. So the columns data is compressed, and because it is in this columnar orientation, the compression factors you can reach are much higher, because it's probably very likely that the values are much closer to each other. And if you, for instance, use delta compression, then this can result in a huge data reduction. So the additional overhead you are adding by using such an index is typically not that large if you, for instance, compare to a traditional B-tree index or something similar. And on the other hand, of course, the compression helps you to read your data much faster, meaning it for sure makes a difference whether you have to scan a whole table with, let's say, a couple of gigabytes or a couple of 100 gigabytes, or whether you have to scan just a few columns where one of these columns might be reduced to a gigabyte or less, depending on how much data is in your table, actually. And last not least, you get a decoupling mechanism, which basically helps you to do ingests on one end, which can be very fast, and do queries on the other end, which can also be very fast. And those queries, they can also then be very demanding. They can go over the whole data you're having in there without necessarily disturbing much your ingestion at the same time. And that then helps to create mixed workloads, because typically the database is not doing a single thing for you. It does multiple things, even if you are, let's say, having very extreme ratios of 90% read, 10% write, or vice versa. So this here helps you to basically stay within a single system, have a mixed workload, and the workload is then also scaling with you. And as mentioned earlier, it doesn't matter much whether the index is currently fully complete or whether it's just like added to. You will always read your complete data set. And in terms of reading that these few additional rows, that doesn't really hinder performance in the end. Now, we also have some downsides, obviously. As already mentioned, the writing, the reading might be much more expensive. So you don't have to maintain your table only, you have to maintain your index as well. Depending on how it is implemented, this can create large overheads. If you're, for instance, also waiting too long to recreate or append to the index, this can be very expensive and can slow your system down in the end. So this is clearly a downside here. And on the other hand, your I/O advantage reduces the more columns you are selecting. So let's say you have a table with 5 columns. You're having a columnar index over all these 5 columns, and you're using the 5 columns all times, then you're effectively scanning the whole table at all times. And what's left from your I/O advantage by compressing and by selecting only a fraction of the columns is essentially gone towards the compression. So there is some advantage, but it's not as high as it could be, basically. But that entirely depends on the usage pattern you are having. And also, as stressed already, the index has to be maintained. It can get out of sync. That doesn't mean, on the other hand, that you're getting false data back, but it means that your query, which could be really fast, might be a bit slower because it has to read some additional rows because the index was not yet up to date. Now, since we are talking about Postgres, and I'm sure you're following the community very actively, the question of doesn't Postgres have this already pops up. And yes, basically there are solutions, but they are a bit different than what we are going to present you. So the first one is ZStore, which is now under the hoods of Greenplum, basically. And ZStore is not really an index, but ZStore introduces a storage engine, which was made possible within Postgres 11 to get additional storage engines, basically, most likely similar ways as MariaDB or MySQL does it. But that also means you have to store your data in that engine. So you can't reuse your native Postgres tables. And native Postgres tables are just great because they have all the features that you know from Postgres. They have the uniqueness constraints, they are proven to work. Any other constraints like the foreign keys, they are proven to work. The wall is proven to work. So you can even do replication on top, and you have your complete backup restore ecosystem. So while this is a great thing to do, you might want to rethink it because you're losing certain advantages Postgres gives you out of the box. The other thing is indeed a true columnar index. It's provided by Fujitsu. It's called VCI. If you Google for that, you will find a white paper, or actually not a white paper, it's more like a data sheet in PDF format. and that describes it a bit more, which is very similar to what we are talking about right now, but it seems to be only available for the Fujitsu Enterprise Postgres. And also it's a more hybrid implementation and therefore targets more in-memory workloads, meaning you effectively use somewhat more RAM to cache your data in RAM to get faster access. And this is just another differentiator to ours. And what I'm going to show you next is how we basically make use of this and how you can think about our columnar index we are adding to Postgres, which is available for the Postgres 11 and 12, the free open source editions, as well as we are providing it for Enterprise DB, Postgres Advanced Server. And what this looks like is like this. So let's just make an example. Let's assume you have a geospatial table with 3 columns. You have a latitude, longitude. They are encoded as double precision, which is just what we picked for the example. You can, of course, use PostgreSQL and then use the point data type. That would work the very same way. But here we basically opted against it to just give you an idea of how this could work. And then we have an additional value field. So this is basically our 3 columns we're having in our table. You see the table above, and it's just a bit highlighted here with the 3 columns and a couple of rows ingested. Now, the next thing we are simply doing is we call create index, because we are talking about ColumnStore indexes. So we are going to call create index, easy as pie. So we call create index on the table, and we tell it explicitly to make use of the ColumnStore index, which is just how we named our feature internally. And we don't have to bother about thinking, oh my God, how many columns do I want now? I just pick all of them. And the index is going to take care of everything else for you. So we're just passing in their lat, long, and value. And then we just complete this command. Then the index structure basically is created. And now in our case, to fill the index, you have to call vacuum on your table. And the vacuum operation here will write the index for you. And then you can make use of it. And you see this on the right-hand side. So from now on, whenever you're querying, you see a parallel S64DA ColumnStore scan on your table with a filter. I omitted the filter here in that case, but like that will show up in your plan. So your plan is going to show you the columns it picked and the filter it applied and how many rows it returned from that. So it's basically just like you're used to it from Postgres, how it typically queries for you. It's just now using a different index, and that gives you a lot of benefits. And these benefits are that we are using direct I/O, meaning you don't have to go to the page cache anymore, and that effectively frees up RAM for you. So typically, if you query a native Postgres table, then this table will be loaded, or parts of the table are going to be loaded into the RAM and then queried from there on, which on the other hand gives you a speed boost, obviously, because once your data is in a page cache of the operating system, you can access it much faster. However, this page cache is eating fractions of your RAM for your query operations. So effectively, your join operations, your group bys, any other aggregates, order bys, whatever you have, they are going to suffer from this. Why? Because they potentially need to free up the RAM again if they need more RAM than there's currently available. And therefore, those pages are going to be flushed out of the RAM. And the worst case that could happen here is you need exactly that page again, which was flushed, which is obviously a somewhat unlikely event because there are cache management systems in there, but this could potentially happen. Then you have to reread the page from storage, and this is going to be very slow. Now, that's why we opted for direct I/O, and we know that today's storage systems are really beefy in terms of throughput, and this is just something we are going to make use of. So if your storage system provides you the capabilities of delivering 6 GB per second, then you can make use of the whole 6 GB per second and read the table just direct without buffering with RAM. And the RAM in that case is then used only for active data you're loading, and therefore you have effectively much more RAM available for your data process. Next point is you can finally use wall replication. That was simply not possible with our foreign data wrapper-based acceleration because we essentially never implemented it. And this is just a very difficult thing to do. Now with the index interface we used in Postgres, the wall comes for free for you. So meaning this solution is going to even scale out. So you're having a cluster set up, then you can just replicate this over. The index will sit on your data nodes and be filled automatically, and then it will just work out of the box. The same goes for backup and restore. If you followed the mailing list a bit, we published a patch actually for the foreign data wrapper interface to include foreign data wrapper tables in backup and restore operations. This patch has been accepted, but it will only be available in Postgres 13, which is kind of around the corner, but we basically published it already 1.5 years ago. So this took a bit of time, which is just the natural process it goes. And with the index on top now, this is just so much more easy because you can rely on your existing Postgres backup tools, which are going to just do the job for you. And we support obviously auto vacuum, which is a really nice feature. So if you're getting new data into your tables frequently or your data is updated frequently, then you can just rely on auto vacuum running in the background, maintaining the index for you, keeping it sanitized and your statistics up to date. That was working for the foreign data wrapper interface, but still it felt somewhat different and maybe a bit clunky. So this is much more drop in here and very lean actually. Now, what this enables you together with all other features we are having is that you essentially get a much more accelerated Postgres for mixed workloads. And we are specifically targeting mixed workloads because, as mentioned earlier, we understand that there's a database, not a single database doing a single job. Databases typically do multiple jobs at once for you. Just the ratio of the mix you're having, that might vary. And in our case, our complete product essentially is now based on 3 pillars in the end, which is query planning, data access optimization, and query execution. And all these three things working together, where the ColumnStore index is now in the data access layer, obviously, give you much better speeds on your Postgres, even if you're not using it predominantly for analytical workloads, but as said, the mixed workloads again, so your data is updating all the time or a fraction of the time, then you can still make use of faster access towards your data. And in a very ideal case, what this looks like is that you have this query, which is here depicted on the left-hand side, consisting of 2 joins, and we have a scan and filter operation. We have an aggregate in there and a sort at the very top. And what typically might happen in current Postgres without any extension is that you get some parallelism on your first operations, and then your merge comes. And after this merge, it might happen that your join is executed sequential, and therefore it runs slow. And the same goes for your sort and final aggregate. And what our solution in the end does is it shrinks this together by adding parallelisms throughout. So we are introducing additional nodes as well, which then take care that your data can stay parallel. And in combination with the columnar storage index, you then also can shrink down the scan and filter. And the scan and filter is what we shrink before with the foreign data wrapper interface. And this is going to be replaced now by the columnar index. Now, let's have a brief look at how it works all together. And then after this, we'll be diving a bit deeper into the index. Basically, I'm going to show you how this works. But now the big picture, I want to conclude on the big picture first. And as Andy already said, we are typically benchmarking with DPCH, and this is query number 6 here. It is like a very straightforward scan only query. There is no join. And that makes it just ideal to show a bit of what's happening inside. And obviously, when you run a query in Postgres, the first thing you have to get is a plan. And that's, in our case, obviously a parallel plan. Plans in Postgres are these days typically almost all parallel, especially if it's like more OLAP or reporting like queries. but the degree of parallelism varies. That is just certain limitations you're hitting here and there, and we are helping this by increasing the parallelism in the end. And the second step is you have a scan. You need to first load your data from disk. And in our case, this would be this columnar scan. So we have basically a table with the columnar index on top. And as the picture suggests, we are only taking a fraction here. So in the example of query number 6, we would need in total 4 columns. And these 4 columns are scanned. And as said, they're directly read from the disk into memory to work on. And what happens next is that they are decompressed in memory, and then we apply the filter. So the complete end chain basically is applied in step number 4, and then the rows we constructed again out of those columns are then selected, specifically reduced and returned as tuples, and then finally on this much smaller data set, you run the aggregate. Now, the additional step of number 4, which says here filter and construct rows, a sort of filtering is already done during the scan, mostly targeting the columns. If you remember the foreign data wrapper, we had a concept called range index or optimized columns. There we pre-filtered rows already, which is not happening here, as we basically typically read the complete column, and you have to think of this as a stream operation. So that does not mean that you first scan the whole thing, then you decompress it, and you're potentially using a lot of RAM for this, and then you filter. No, this is a complete stream operation. So 2, 3, and 4 basically work as a single block and essentially only result in having the table of number 5 in RAM. And this is, as you can see, much smaller, so you're not using that much of the memory. Now let's talk a bit more about the index. And I'm going to stress TPCH again, because this is just something we know very well and we can talk about a lot. And we also know how we can compare it to the foreign data wrapper and the other things we have done so far. And probably most of you know this already. So we have here the schema, as you know. It's essentially somewhat star-like. There are 2 really big tables, line item and orders. And for the next few slides, we are taking just another query, which is a little bit more involved than query number 6, and this is query number 14. And as you see, query number 14 is not only doing scans, obviously, but it's also doing a join. And the join is happening here on part keys, and you basically calculate a certain revenue, which is then even based on a condition with like a promotion condition, basically across a time range of 1 month only. And we're just going to look at this. So just pretend that we're having this data set loaded onto a machine with Postgres 12. And the first thing we are going to do is we run this native. So with the best schema we know for Postgres, with all indexes on top we know and which are allowed by the specification, and we're just going to run this query. And a couple of seconds later, we get a nice plan. And the plan in this case looks like this. We see this is nicely parallel. You see the shades here on some of these nodes, hinting for parallelism. And only after the first aggregate, this plan goes sequential. So you have the gather node, which is sequential, and you have the final aggregate, which is also sequential. Now, if we look at this from a time perspective, then we notice that the whole query takes 15 seconds, 16 seconds rounded up. And a huge fraction of this is the scan time rounded up to 14 seconds roughly. So this query, after all, although it contains a join and contains an aggregate, is after all very, very scan heavy. And the next step which we're doing now is we're just going to call create extension, because the extension we deliver for Postgres already gives you benefits in terms of parallelism and introducing additional nodes to keep your plan parallel if it can. And we're just going to see what's happening next. So this is the plan after calling create extension. And as you can see, we halve the time. The total query time is gone down to 7 seconds, rounded down, where the scan time still is a huge fraction. So we have 6 seconds of scan time. And now the question is, can I add some structure to my data in order to reduce the scan time even more? Because obviously we try to optimize everything around the join and everything around any parallelization patterns. So this is using much more workers here already. We have here 16 workers. Before it was 12, I guess. So this is running somewhat faster, but I want more speed. And the answer to that is ColumnStore index all the tables columns. And this is exactly what we're going to do. So we just take our schema and we're just using a really straightforward approach, and we call this create index statement on all tables we're having in the TPCH schema. And we are not going to bother with which columns to pick. We are just using all the columns of the tables. So for instance, if you're having this for your line item table, you use all the columns of your line item table. On the orders table, you use all the columns of the orders table, and so on and so forth. And once you're done, once these foundations are there, and you know you already have data in, you just need to create this index once, or you have to wait for auto vacuum. So you will calling vacuum. And once this operation is finished, the index is there, and we can just run our query again and see what's happening. And as we see, we reduce the runtime again. This time we are at 5 seconds roughly, and the scan time just halved. So we shaved off half of the scan time again. And now imagine that this is just a scale factor of 100 gigabytes of raw data. And typically our benchmark is a terabyte. And on 1 terabyte of data, this looks so much more different. So as you see, query 14 is here located in the beginning of the last third roughly. This is a speed up of 30x. And this, of course, varies a bit with the machine you're using. But after all, this is commodity hardware. It's a 2U server with 144 vCores and a bunch of SSD disks delivering really good performance. And as a result, you get all 22 TPCH queries in 80 seconds or less. Now, what we can do is we just take this result and turn it upside down once, and we get to a slightly different representation of the case. And this is now density centric, because we were talking all the time about mixed workloads. So the queries I just shown you are read-only queries, obviously. So let's talk a bit about the density when we get back to the whole picture, basically. And effectively what that means, this solution is going to reduce your CPU cycles. Why? Because you're going to have less query runtime effectively. That doesn't mean that you're seeing less CPU utilization per time, basically, but you're seeing less CPU utilization over time. And the same goes for the RAM. Why? Because you don't have to use your page cache anymore. The data is as said read directly from the disks. You just have to take care that your disks are strong enough. Typically, you can achieve high speeds with already a single NVMe drive these days. And the same goes for your I/O, because since we're compressing that data, you're effectively using less I/O. And in a nutshell, this calls for a 4 times increase of concurrent users or query, meaning on your existing system with that extension and the ColumnStore index on top, you can run 4 times the users or 4 times the queries. And with that last slide, I'm going to hand back to Andy, and thanks for your attention.
Thank you, Sebastian. Okay, so we're going to, if people have questions, again, feel free to enter those into the questions panel. We have a few already. Next slide. One of the questions we get quite often is, how much does Swarm cost? So we charge based on the number of cores in your server, very modest, $33 per core per month. It usually is less than the cost of a hardware upgrade, and certainly a lot easier. As Sebastian mentioned, we work with Postgres, free open source Postgres versions 11 and higher. Also work with the EDB versions of Postgres as well. Ideally on Linux, and with a few people using it on Windows, but we usually advise Linux. The next slide, please. Thanks. Question we get quite often is, tell us about migrating a, kind of the development project or migration project. Swarm simply extends what Postgres already does, just makes the query performance in Postgres quite a lot faster and makes it more efficient from a resource utilization perspective. So, but yeah, we don't really change the way Postgres is worked or used or what it's compatible with. So the timeline for developing a Postgres application is mainly unchanged by the use of Swarm. It's as fast or as time consuming as it normally is. And the only difference is maybe in the any time you'd have to spend tuning, with features like the ColumnStore indexing and the increased parallelization, just make more queries perform faster out of the box with less tuning. So from that perspective, you might save some time. And then lastly, if you'd like to try Swarm, you can do so for free. We have just ping us or go to the Amazon Marketplace, AWS Marketplace, and start up a Swarm accelerated Postgres instance from there. If you want to run it anywhere else, any other cloud or on premises, just ping us and we can hook you up with that. And now turn it over to some of the questions we've had. First one is, are there any, with the ColumnStore indexing and maybe even the parallelization, are there any database design considerations? I know there are with the parallelization, and that's the topic of our next webinar early in September. But for ColumnStore indexing, really a lot of the benefits of the acceleration that Swarm extends Postgres with is to really make Postgres a more forgiving, or as one of our engineers puts it, user resilient database, so that Postgres chooses to do the best possible thing, even if the DBA doesn't. But I'll let Sebastian give a probably better qualified answer to design considerations for ColumnStore indexing and whatnot. Anything to add?
Yeah, so maybe quickly on that topic, because it's really interesting. It just really boils down to create index, and then if you have data already, you're on the safe side to run vacuum once, and then rely on auto vacuum. And if your auto vacuum is tuned properly, then all the incoming data and all the change data is going to be written to the index automatically. And as said, if it's not always up to date or in sync, let's put it like that, but you will be always querying all your data. So there is no harm done here, no false results. And we are currently testing a bit more in terms of how far can we stretch it. And think we'll be having very likely demo around this as well to see that also these hybrid cases, which Gartner calls HTAP, that they are working like they should, and like we demoed also with the front data wrapper interface. But in the end, this is just so much more easier to use here right now, because you just add your index, you rely on Postgres for everything else, and then you get faster queries, and that's it.
Thanks. We have another question about the pricing. Is the per core pricing for production, or is that applied to development and QA as well? Great question, because we do have another offering we call the lab license, which is ability to use Swarm in non-production use, and that comes out to about $550 a month, and it's not based on the number of cores, it's based on the number of databases. So if you want to use get started with Swarm for development or testing, benchmarking, it's a good way to do it, and gives you access to people like Sebastian, who can give you advice on how to get the most out of it from a support standpoint. Another question, Sebastian, is Swarm available on Amazon Web Services? Any plans to integrate with RDS Aurora?
No, it's not. It's available as an EC2 instance. And I think, Andy, you can answer this much better than me, actually.
Right, sorry, Swarm is available on, it's available on AWS in the marketplace. So you just install it from there, integrated with your billing and monitoring and everything else. Or you can, like I said, you can install Swarm pretty much anywhere Postgres runs. But in terms of just sort of spin it up from the Amazon marketplace, we do that, and we run on pretty much your choice of AWS instance. Integrating with RDS Aurora, no, not yet. Neither RDS nor Aurora allow you to install extensions into Postgres, so that really eliminates the ability to run, extend either of those services with Swarm. So when we're running on Amazon or any other cloud, it's really, kind of hosting your own, running your own version of Postgres. Okay, did that answer that? Let's see. Would the ColumnStore indexing work on JSON B columns?
Yes. So there's no restriction on data types you can put on. You can have JSON B columns, straightforward, simple JSON columns. You can go with numerics if you like, PostGIS data types, anything you want. So there's really no restriction. The let's say the caveat is more whether you can early filter on these. But typically what we've seen so far in our experiments and measurements, you don't really need to do this because the whole column as said it's just compressed and read again. And this is fast enough to give Postgres the ability to filter out on the go, basically. So no restrictions on that end.
Thanks. And let's see, is the order of the columns in the create index important?
No, it doesn't matter. The restriction here currently is that we support up to 32. So if your table has 32 columns or less, you just add them all. Order doesn't matter. The index is going to take care of this also when querying. However, if you're having more than 32 columns, you need to see a bit what you're going to use. Maybe you're dropping comment columns, which you typically don't query on. But yeah, order doesn't matter. Just create it.
Thanks. And really time for one more question. There are other questions. I'm sorry we didn't have time to get to all of them. We'll follow up separately on some of the others. But I think I answered this one. But question was, if you want to try it, how do you install it? Again, go to the AWS marketplace and search for Swarm64 and install it there. There are 2 versions in the marketplace. Just be sure and install the there's one that runs on the FPGA accelerated, or the FPGA instance, the F1 instance on Amazon. Don't use that one. Where I'm talking about the one that runs on the CPU only instances. That's less expensive and probably just as fast for most workloads. And any other platform, just ping us and we'll get you an installation package, and Sebastian can help you get that up and running on new or existing Postgres databases. Okay, so actually here's a really good question just came in. What about performance for queries that use the like operator?
Yeah, we used to accelerate this with the front data web interface. It is not directly accelerated anymore. However, again, due to the compression and the selectivity on columns, this is going to be faster than on typical native Postgres. Plus, whenever it comes to like acceleration, Postgres does an excellent job, by the way, with TS vector and TS query. So like full text search, which is a really good thing.
Great, thanks. All right, everybody, I want to thank you all for joining us today. Thank you, Sebastian, for sharing your wonderful knowledge. And we look forward to seeing all of you again online. I think September 2nd or 9th, I can't remember which, is our next webinar, and that'll be on parallelism do's and don'ts in Postgres. Try and get the most out of parallel processing in your Postgres servers. Again, thanks to all of you for joining us, and wish you a good rest of your week.
Thank you so much. Bye.